So this is a very short video. It's going to talk about, I want to talk about the similarities between how we look at measures of dispersion when we're looking at a sample versus a population. So in a previous video, what we did is we looked at the development of a measure of of variation. We looked at two specific measures. We looked at a population variance, and we developed that formula and said it's going to look something like this: sum of all values x minus the mean squared divided by my number of observations. And then we developed the population standard deviation, which is, again, we see all over the place in a number of different fields. Sum of all values, x minus the mean squared over n. That's where we left off. But now the extension of this, and especially into the world of statistics, which we've talked a lot about the fact that generally we're inferring things about the population. So this is a luxury to have this kind of data available. Where we're generally going to spend our time in statistics is in the world of inferential statistics dealing with samples. So if we look and extend this out to the same idea, this measure of dispersion, this and now this sample variance, that formula looks something like this. Now we've got sum of all values x minus the x bar squared divided by n minus 1. So of course we've got the variables that are different, because now instead of dealing with population parameters, we're dealing with sample statistics. And so we see the substitution of the S for the lowercase sigma and the X bar for the mu. All right, but the big difference, of course, and the obvious difference is down here, the mathematical difference. The only real tangible one in here is this n minus 1, which is our degrees of freedom. We also see the same difference when we look at the sample standard deviation. So again, if we take the square root of each side of this equation, we're going to have this sum of all values x minus the x bar squared over, again, n minus 1. So this holds for both of our variance and our standard deviation. Now, the way that I guess I would explain this, same progression, but the way that I would explain in the terms, the degrees of freedom, currently in the context of statistics in this one is, imagine the difference if you have a sample size, of, we'll say 1,000, right? Then this n minus 1, we're comparing kind of 1,000 versus 999 in the denominator. And I don't think you'd ever see a statistician write this up this way, but in my pragmatic world of statistics, I think it's pretty persuasive. But this is a much different kind of impact on our numbers or our calculation than if we had a sample size of 5 and we have n minus 1 as a sample size. Kind of the difference in scale and scope and size in our denominator here is significant. And so we see these degrees of freedom have a much greater impact when we have a low sample size, right, this n minus 1, than we have a large sample size. So again, if we looked at a comparative set of numbers, imagine it's the same value on the numerator kind of in scenario 1 versus scenario 2. And I think it's a very pragmatic look at statistics. It's one of the things I like about statistics is we can see the development of those kinds of ideas throughout. That is the primary difference, right, in terms of the calculation of these measures of dispersion between a population and a sample. It does kind of highlight the difference between the right and the wrong answer, but we can kind of see the impact and how those work out with that degrees of freedom in the numerator when we have varying sample sizes or numbers of samples completed.